Okay, so welcome back, Trig students. So we've already got college algebra behind us, and now we're starting on college trig. You know, I hope you enjoy this class. This first podcast that I have is going to be a recap of things that you already did in your first class, and then also you'll have some notes of things that you'll be doing in the second class. It's very important then that you know the vocabulary and stuff, so I think what we'll do is we'll start off with some definitions. And just make sure that you know what all of these mean, because we use these terms over and over again. So if you're kind of confused on them, then it just kind of snowballs. So this is very basic stuff. So all of these definitions are very important. Let's start off with initial side. The initial side is the starting side for an angle. So if I have this angle, and we're starting here and going here, this first side here is the initial side. So this is the initial side. And where I end, which is this right here, is the terminal side. So that's all there is to it. Initial and terminal. Okay? If I take that angle though and I place that angle on a coordinate plane such that the vertex of that angle is at the origin, and I slide this initial side over to the positive x-axis here, then here's our angle in standard position. So we could not have an angle, for example, like this. That is not in standard position because, depending on which is the initial side, but neither one of these sides lies on the positive x-axis. Okay. We will also talk about the difference between positive and negative angles. Positive angles are angles that go counterclockwise, whereas negative angles travel clockwise. So if I drew this angle here, and we're going from here to here, that's a negative angle. And this angle would be a coterminal one to that one, but it is a positive angle because I'm going counterclockwise. All right, now I just talked about coterminal then. So coterminal angles are the angles with the same initial and terminal sides, just like I drew there. So let's take another one. Let's say we have this angle here. I'm going to start here. This is my starting side, and I'm going to end here. Okay. So initial side, terminal side. Well, let's start here on this same initial side, but let's travel this direction, and let's end right here. Well, those two angles are coterminal to each other because they start and end in the same place. There's yet another angle. Let's say this angle. I'm going to start here, but I'm going to go all the way around the circle once and then end there. Well, there's another angle that is coterminal. So notice how we could just keep doing that. We could go 2 times around the circle and then back up to that terminal side. So that would be another angle that's coterminal with it. Central angle, that's a term from geometry. And that's an angle that we sit in a circle with the vertex right at the center of the circle. So this angle here is a central angle. All right, so those are some basic definitions. There's a few more, though, that are going to need their own page. So, for example, radian measure. So you're used to degree measure, but we are going to talk about not only degree measure, but radian measure, and we're going to talk about revolutions, like how many times or how many fractions of a time you go around a circle. And so we have to be able to convert back and forth between them. Remember that a radian measure, if you would take a circle of any length, of any radius, I should say. So here's a circle, here's the radius. Whatever that length would happen to be, if we would take that length of the radius and wrap it around the circle, so we're forming an arc, and that length of that intercepted arc is the same length as the radius, then that central angle formed is 1 radian. With degree measure, you put this little degree sign up here. A radian, you can put a little superscript of an R, but actually your textbooks and stuff, they drop that R very quickly. And if you see a degree, then you know it's in degree. If you don't see a degree sign, then you know it's in radians. So that's the definition of 1 radian measure. Now it doesn't matter how big the circle is. Let's say I just double that radius, and we draw our circle. And I take the length of that new radius and I wrap it around an arc. Well, it's going to end in the same place as this one. So that central angle is 1 radian measure. So it doesn't matter on the size of the circle. Okay, it's whatever radius you have laid out on the arc of a circle, it will give you that same angle, 1 radian. All right, we have a formula then that we use, which says an angle that's in radian measure. So what I have here is an angle, and this is the Greek letter of the alphabet theta, and you're going to see in trig that we use a lot of variables where we use the Greek letters of the alphabet, so it's not a big deal. It's just like an X or something, but this is referred to as theta, and the radian measure is equal to the arc length divided by the radius. Okay, so let me show you how this works then. If we have a circle with a radius of 1, you know from geometry and earlier studies that the circumference is 2 pi r. So our circumference on this circle would be 2 times pi times 1, so it would be 2 pi. Okay, so the radian measure then is our arc length. Well, our circumference is our arc length. Our arc length is all the way around the circle. Okay, so the arc length is 2 pi. If I divide 2 pi by our radius of 1, then I get the angle measure in radians. So 2 pi is 1 complete rotation around the circle, so it's equivalent to 360 degrees. So 1 revolution around a circle of radius r corresponds to an angle of 2 pi radians. So 2 pi radians is equivalent to 360 degrees. Okay, sketching and finding coterminal angles. Let's start with, an angle in degree measure. And let's say we have a 60-degree angle. Okay, so this 60-degree angle, it's actually, we're starting over here, so this is our starting point. Here is our terminal side, initial and terminal sides. So a coterminal angle is any angles that start and end in the same place. So 60 degrees, there's one. Well, let's start on the same initial side, but let's go this direction and let's end over here. So notice they have the same starting side and ending side, but this angle went clockwise, so that's a negative, and we headed around a circle, and we didn't get all the way around the circle. We got 60 degrees shy of all the way around. So 360 minus 60 is 300 degrees. So those two angles are coterminal to each other. Let's take this angle. Let's say we have an angle of 120 degrees. Okay. So the angle is starting here, it's ending here. Here's my initial side, here's my terminal side. Well, let's start in the same place, and let's go in the same direction. Let's go all the way around the circle and then back up. So those two angles started and ended in the same place. The first one was 120 degrees. The other one, we went all the way around to this circle, plus another 120 degrees. So we're at 480 degrees. So 480 and 120. They are not angles with the same measure, but they are coterminal. What would this angle be if I start here and I end here? So think about that for a little bit. That would be a negative 240 degrees. And we will do the same thing in radian measures also. As we get more comfortable with radian measure, we'll see how that we can name coterminal angles there also. Let's go to conversions between degrees and angles. So remember we said that 360 degrees is equal to 2 pi radians. Or, if I divide both sides by 2, I get pi radians is equal to 180 degrees. Halfway around the circle is pi radians. All the way around the circle is 2 pi radians. So we can use that then to convert back and forth between angle and radian measure. So if I give you, let's go with 90 degrees. So if we start off with an angle that's 90 degrees, let's use dimensional analysis like we do in science classes. So 90 over 1, because these are equivalent. Let's take this one here. 180 is equivalent to pi. So I can write that as either pi over 180, or I can write it as 180 over pi. Since those are equivalent, that's equal to 1. I want to get rid of the degrees, so I'm going to choose the one with the pi over 180. So then the degrees are going to cancel out, and I have 90 pi over 180, and I can reduce that fraction to pi halves. So pi halves is the radian measure for 90 degrees. So it's equivalent to 90 degrees. Let's take 240 degrees. We want to convert 240 degrees to radian. Alright, so I want to get rid of the degrees, so I'm going to take the pi over 180. The degrees then cancel. Now I have 240 pi over 180, and we're going to reduce that fraction. Let's divide by 10, and 24 and 18 I can divide by 6, so we get 4 pi thirds. So 4 pi thirds radians is equivalent to 240 degrees. Okay, let's convert a radian measure. Let's say we have 3 pi halves. Okay, so we're going to put 3 pi halves, that whole thing, over 1, and then we're going to convert. We want to get rid of the radian measure, so we're going to choose this one here, which has the radians on the bottom. So we're going to multiply by 180 over pi. Well, these two are in radians, so remember that radian cancels out. We can also reduce out a pi, so we have 3 halves times 180. Okay, well, let's divide by the 2 first of all, so we'd get a 90, and then 3 times 90 is 270 degrees. So as long as you remember a conversion, either the 360 is equal to 2 pi or the 180 is equal to pi, it's easy to convert back and forth just by using dimensional analysis. Okay, let's take a look at arc length. So I gave you that, I gave you the formula for the angle measure. Remember, I said the angle measure in radians. Oops, I need to grab. Sorry, let's go back down here. Arc length. So remember I gave you this formula earlier. I said an angle in a radian is equal to the arc length over the radius. Well, here's that equation again, but it's just solved for the arc length. So we want to find the arc length. So an arc length is in a circle. That's like maybe from here to here. This would be an example of an arc length. We want to know how far it is between those 2 points, or what the length of that arc is. Okay, so we're going to use this formula where the arc length is equal to the radius times the angle. But here's the kicker: the angle has to be measured in radians. Okay, I'm going to work a problem actually 2 ways. I'm going to do it the way you would have learned how to do this in geometry, and then we're going to try using that formula. Okay, so find the length of an arc intercepted by a central angle of 240 degrees. Let's draw a circle. Let's go 240 degrees. So I'm just going to start here, and this would be about 90, right? This would be 180. I want to go more than that, so 240, maybe something like that. So this would be 240 degrees. So I want to find the length of the arc from here all the way over to here, given that my radius is 4. So we're looking for arc length. Well, arc length is a fraction of the circumference. So can you tell me what the circumference of the circle is? Circumference is 2 pi r. My radius is 4. So 2 times pi times 4 is 8 pi. So all the way around the outside of that circle is 2 pi radians. Well, I don't want that far, do I? I only want 240 degrees out of 360. So I want to go 240 degrees out of a total 360 degrees. Does that make sense? So I don't want the arc all the way around the circle. I only want the arc that goes 240 out of 360. So if I reduce that down, I get 2/3 the length of the circumference. So we need 2/3 the circumference, and we said the circumference was 8 pi. So our radian measure is 16 pi thirds, it looks like. So that's a way you already know how to do it from geometry. Now let's use our formula here. So our formula says to find the arc length, we take the radius times the angle, but the angle has to be in radians. So the first thing we have to do is convert. Our angle is 240 degrees. We've got to convert it to radians. So 180 degrees is equivalent to pi radians. So we multiply, we do our dimensional analysis then, and we see that we can reduce by 6, so we get 4 pi thirds. So that represents our angle in radians. So now we just have to take that times the radius, and our radius is 4. And when I multiply, I get 16 pi thirds. All right, so you can either memorize the formula, use this new formula, or if you forget, you can always convert, use what you did in geometry several years ago. All right, so there's arc length. Angular speeds. Angular speeds. For angular speed, you're going to see that they're going to use this crazy letter of the Greek alphabet, which is omega. So omega, or the angular speed, is the measure at which the central angle is changing with respect to time. All right, so notice it doesn't have anything to do with the size of the circle. It doesn't say you multiply it by the radius or anything, right? So radius has no bearing on angular speed. So we have this Ferris wheel here, and it has here's our Ferris wheel. It has a 50-foot radius. Here's our radius. This is 50 foot here. But to find our angular speed, we don't, whoops, I put degrees. We don't care what that length is. We know that it's going 1 and a half revolutions every minute. So we want to find the angular speed in radians per minute. So we want to convert the revolutions to radians. All right, so how do we do that? Well, we know that 1 revolution is equal to 360 degrees, right? And we know 360 degrees is how many radians? Hopefully you said 2 pi. So that means then that 1 revolution must also equal 2 pi. So I want to convert 1.5 revolutions to radians. So if I'm going to use dimensional analysis, 1 revolution is equal to 2 pi radians. The revolutions cancel out. Looks like I have to multiply 1.5 times 2 pi. So we get 1.5 doubled is 3. So our angular speed is now in radians per minute. Okay, so that's how you would convert. The key thing to remember, angular speed has nothing to do with the size of the circle. Has nothing at all to do with it. Okay, we just want to know how fast is the angle changing with respect to time. Linear speeds. Okay. A linear speed, and here we're just going to use the letter V. Oops. For the linear speed is the V. It's the length of the arc. So what we were talking about before, you know, with the central angle and the length of the arc, is the length of the arc that we're going through with respect to a single unit of time. Okay, so we have a Ferris wheel. We have the same problem again. 50-foot Ferris wheel. And we are looking for, it's making 1.5 revolutions per minute. Find the linear speed. Okay, so the linear speed, if we use this formula up here, remember we said that the length of an arc is equal to the radius times the angle, but that angle has to be in what measure? Has to be in radians. So we take our 1.5 revolutions and we've got to see how many radians that is. Well, let's write this out again. 1 revolution is equivalent to 360 degrees, which is equivalent to 2 pi radians. So then we said 1 revolution is 2 pi radians. So we want to get rid of the revolution. So we put 2 pi radians over 1 revolution. Those cancel out. And we get 3 pi radians. That's our angle. That's our angle measure in radians. So to get the arc length then, we take the radius
Mr. Colford, please come to the main office.
Times that angle.
Mr. Colford, to the main office.
So we get 150 pi feet per minute. And if you want to change it to a decimal, it'd be about 471.2 feet per minute. So when we're looking at linear speeds, now that does have, how big your circle is, does have a bearing. Because if your angular speed is not changing, when your circle gets bigger, then your point on that circumference is going faster. And we can kind of outline that in class too for you a little bit better. Okay, one last thing we have to do is the area of a circle. Here again, the area of a sector. This is something that you did in geometry. Here's a new formula that we have for you that you can use. Once again, to use this one, it's important that your angle is measured in radians. So it's kind of nice to know that anytime you're going to use any of these formulas, the angle, you can't have it in degrees, you can't have it in revolutions, you have to convert it to radians. Okay, so read through this problem. I'm going to draw a diagram. So it's spraying water. So spraying water out 70 feet. And it's covering this section, so this is referred to as a sector. So we're looking for the area of that sector. And a sector then is a fraction of the area of the whole circle. All right, so to figure out what this is, then we're going to use that formula. Area is equal to 1/2 radius squared. I keep putting degrees there. It's 70 feet, so our radius is 70, and we got to square that, times the angle in radian measure. Well, guess what? It's not given in radian measure, so we got to convert 120 degrees to radians. Okay, well, we know 180 degrees is 1 pi radian. So the degrees cancel. We can divide by 10. Then we have 12 and 18. We can reduce by 6. So we get our angle in radian to be 2 pi thirds. So then we put in that 2 pi thirds. And then we can simplify it all the way down. And I think if you multiply it out, remember it's 70 squared, 70 times 70 times pi divided by 3, you should get 5,131 square feet. So that's the area of a sector. Okay, I think that takes care of everything that we need. Hopefully you can use this, and it will help you with problems that you have, and you can always refer back to it. All right, good to have you back in class. See you in class.